you can stop by the exhibit hall. They've got all of them up, and it's just very exciting and enlightening. Okay, our first transhumanist speaker is a kind of pessimistic guy. We're all about human space exploration, and his slant is slightly different. But we want to hear from Ben Goertzel. He's with Humanity Plus magazine, plus other places. So give yourself the plug to what you're doing, Ben. And by the way, this is our first try at a transhumanist track at an ISDC. And we're planning on having a full day, hopefully, in San Diego in 2013. And we'd love for you to all of you to join us.
By the way, how long should I talk for, given the various schedule limitations?
How long is your talk?
Well, it depends on how long you want to do.
About 45 minutes, 50 minutes. We're going to go over and then
Yeah.
it's okay.
All right, I may go less than that. We'll see how it goes. Oh no, I have the ability to rattle on endlessly. Having been a former college professor, but I don't think it's necessary.
Well, we're going to have a little time for questions.
Yeah, actually, I'm happy to leave a lot of time for questions. This stuff is just fun to talk about.
Sure.
So I'm not really a space researcher. I'm an artificial intelligence researcher, and I'll give a brief introduction of myself since I was asked to. So I have a PhD in mathematics from the 1980s, a long time ago. I was a professor in math, computer science, and cognitive science. And since the late 90s, I've been in industry doing consulting on artificial intelligence for government agencies and for commercial companies. I lived around here for a long time. Now I'm mostly based in Hong Kong and leading a bunch of AI projects there, both aimed at the grand goal of AI, of trying to build computer programs that can think like people or better, and using AI to do various particular things like analyze genetics data, try to predict the stock market, and a whole bunch of applied projects. I've been interested in space literally as long as I can remember, because my first memory is watching Neil Armstrong walk on the moon. Because I was like 2 years old then, in the late 1960s, and all the adults around me were staring at the television, watching this black and white picture of these people in weird suits bouncing around. And that looked cool. I was intrigued just because everybody else around me thought it was so important. I didn't understand why it was so unusual to be hopping around in the moon. It seemed like a natural thing to do. So, like many nerdy kids of my generation, I grew up thinking I'd be an astronaut until I realized that my eyes don't work well enough. You need to have good vision to be an astronaut. So I became interested in astrophysics and various space-related aspects of science until eventually I decided that was too slow-moving, and I got into artificial intelligence instead. I like that because in AI, if you have the right idea, you can just sit down and type and create a thinking machine that's smarter than you. Now, I've been trying a long time and I haven't succeeded yet, but at least in theory, you can just sit there and do it and program it. Whereas going into space seemed like it took a lot of money and orchestration of resources from all these big organizations and so forth. It's getting a little bit less that way now with the commercialization of spaceflight, but in the 70s and 80s, it was certainly very much that way. One of the reasons I was interested in space as a kid actually was that, in the 1970s, we didn't have the idea that the singularity could come in our lifetimes and bring us immortality and superhuman AI and nanotech and femtotech and all this amazing stuff. You read about all this stuff in science fiction novels and it seemed like, damn, I'm not born at the right time. I'm not going to live long enough to see superhuman robots frolic in space and all these amazing things. So, maybe the best plan is to build a spaceship that can travel at near light speed and kind of zoom away from the Earth, come back in maybe 1 million years, making use of special relativistic time dilation. Then, of course, when you come back, all those idiots on the planet may have nuked themselves, and you find yourself on an empty planet with a bunch of radioactive mutated cockroaches. But on the other hand, you couldn't go back to an amazing future society. And this sort of thing was, of course, envisioned in many science fiction novels, like Beyond the Stars by Stanislaw Lem, to name just one. In any event, I've proceeded with a career on AI research. I've always been interested in space sciences in a background level. And I've been very happy to see in recent years some of the trends that have been talked about a lot in the talks earlier today, in terms of space exploration and space exploitation in various ways, mining the moon, asteroids, satellites, becoming something that like regular people can do in small companies with relatively modest amounts of money. I mean, it's still not literally something you can do in your garage, like build a software startup, but at least it's something you don't have to join the military, right? You can have bad vision. You can. There's a lot more options that are out there now for getting into space technology than used to exist, which I think is very positive. So what I'm going to talk about now is artificial general intelligence, which means AIs that can think with the same generality as people, and whole brain emulations. That means human minds plucked out of the brain and put into robots or computers in space. Of course, this is quite a speculative topic, since we do not yet have any artificial general intelligences, nor any whole brain emulations. But nevertheless, my firm belief is that these are the guys who are going to be sprung out from Earth into the universe. I don't think it's going to be bags of meat like we are right now, because these bags of meat that constitute our present mode of being are reasonably well adapted to live on the surface of the Earth, and are not very well adapted in multiple ways to living in space. Whether this prospect disturbs you or not really depends on how attached you are to A, being the ones who go into space for a long time yourselves, and B, keeping the same physical form that you have now, rather than becoming a robot, for example. Because, robots have a lot of advantages in space. For one thing, they won't necessarily get bored when traveling for extremely long periods of time to other star systems. I mean, they don't necessarily have an emotional and physiological rhythm that's based on living on Earth for a certain number of years and having a certain type of stimulation. I mean, they don't need air. They don't need food. They don't need water. They do need electrical or some sort of power, but there's a lot of ways to get power in space. Computers tend to work better when kept cool. They don't necessarily mind being around absolute zero. The electricity may go faster through them. So there's a lot of reasons why once we have engineered systems or uploaded minds in a digital substrate, there's a lot of reasons why they'll just have an easier time coping with space than the human body. Even now, of course, a lot of space exploration is done by machines, even though all we have now are pretty stupid adaptive control systems. So it's hard to see on a purely economic basis how it will make sense to send human bodies up into space once there's an alternative. So I'm going to review a few topics here. One, I'm going to talk about what is AI, what is artificial general intelligence. I won't go too deeply into it because this is not an AI conference, but mainly I want to get across the point that there is a serious research community now focused on trying to make computer programs that think like people, and then even better. And I'll talk for 5 minutes or so about my own research project in that direction. Whole brain emulation, again, I'll say enough about that to get across the idea. That's also a serious research direction now, making computer programs that emulate human brains. I'll venture briefly into the domain of virtual realities, because I think that's one possibility of what the hell do you do while you're like sitting in a spaceship for a really long time, flying across the galaxy. I mean, one thing you could do, you could just sit there like the uploaded human at the end of Greg Egan's novel Diaspora, just sit there and prove mathematical theorems one after the other. And then at the end of his novel, you have an uploaded human being who finds himself alone in some universe, with his mind in some satellite, and there's just blackness around. What does he do? He starts enumerating all mathematical theorems in order of their length, and prove one, prove the next, prove the next, prove the next. What else do you do stuck in the middle of space? None. A human might find that boring. Fortunately, the AI is able to rewire its own motivational system, so it thinks it's really fun. But an alternative, of course, would be to make a simulated fantasy world like the Matrix and just romp around in it. And then by the time you finally get to the other end of your journey, you completely forgot why you got on there because you're having so much fun in the Matrix en route. And the last topic, I'll get you even weirder and suggest some possibilities regarding AIs that may already exist out there in space in various forms. So first of all, what is AGI, Artificial General Intelligence? Well, the AIs that we have now are mostly what I would call narrow AI systems, meaning they're very good at carrying out some particular task, like, say, driving a car, or playing chess, or finding credit card fraud in a database, or serving up search results. They can be much smarter than people at doing those particular things, but yet they lack the human ability to generalize from one context to another. And they can't deal with new things that they weren't programmed for. For example, if you took Deep Blue, the world's best chess player, and you wanted to teach it to play a slightly different variant of chess, say Fisher random chess, where you randomize the position of the pieces on the back row, you would then have to rewire Deep Blue. You'd have to reprogram it in order to get it to do that. Whereas to take a good human chess player and teach them to play Fisher random chess, you do not need to perform brain surgery on them, right? They can learn and they can adapt. Because we have an ability to generalize. We have the G factor, as psychologists would call it. Now, we're not completely general intelligences by any means. We're heavily adapted to the bodies and environments that we grew up in. But we're much more general than any of the software programs yet built. We can achieve a variety of different goals, a variety of different environments. I think we can build computer programs that will do that. We just haven't gotten around to it yet. I've organized a series of conferences of researchers working toward this. The last one had a couple hundred researchers and was at Google's campus in Mountain View, California. The next one will be at Oxford at the Future of Humanity Institute in this December. So if anyone is interested to find out the cutting edge of AGI research, come to Oxford in December. We'll look up AGI 12 or more. And then in 2013, we'll do it in Beijing, China, which should be interesting. So, this is a diagram inspired by the work of the cognitive scientist Aaron Sloman, which is a sort of very high-level view of what happens inside a human-like mind. It doesn't tell you that much, but it's a place to start a discussion. I mean, what things can humans do? They can perceive, they can act, they can be reinforced if what they do is regarded as good by their body's reinforcement systems or bad. They can react automatically to things in the environment. They have a long-term memory, and they have a short-term memory, which we call the working memory. They have certain motivations to guide their selection of actions. They have sort of reflective, deliberative thought processes interacting with their long-term and working memory. And they have metacognition, the ability to think about thinking. And each of these things is done by different dynamically assembled and ever-changing networks inside the brain. To build an AI that can do these things, there's a number of approaches. One of them is to try to emulate how the brain works, which gets into whole brain emulation, my second topic. The other of which is to try to use best-of-breed computer algorithms to carry out the same basic functions that the human mind does, without necessarily trying to emulate how the brain does things in particular. And the latter approach has been my main focus as a researcher, not trying to emulate the brain, but trying to make algorithmic systems that can carry out the same basic functions as the human brain, but taking advantage of the advantages of a digital computer when you can. So for example, if you ask me what's 9,733,006 divided by 8,402, I would either sit there for 10 minutes, take out a calculator, take out a piece of paper. It takes a while. Computer can do that right away. You could, if you made a whole brain emulation, a simulation of the human brain on a computer, it would also struggle to figure that out because it's acting like a brain. But I don't see the need to constrain our digital computer-based minds with all the particular kinds of stupidity that the human mind has. You may as well take advantage of the intrinsic capabilities of a computer in making an AI. So, I'll give a few brief slides telling some of the things about my own AGI architecture, which is called OpenCog. If anyone is interested in AGI in particular, you can go to the website opencog.org, which is pretty disorganized, but you can follow the links from there. For the long-term and working memory of OpenCog, we use a data structure which is it combines a neural net and a semantic net aspect. So it's a bunch of nodes with links. It's a weighted labeled hypergraph for those who like mathematics. There are many kinds of nodes and links. And it stores knowledge in two ways. One is nodes and links could represent particular things. The other is knowledge could be represented by the overall pattern of activity in the network of nodes and links. We have both kinds of representation. So in the explicit kind, like you could have a node for the word cat, a node for the concept of cat, a reference link saying that the concept node links to that word node and so forth. And that is our kind of standard semantic net style of representation that you'd study in an AI class. On the other hand, you can also have patterns of activity spanning large numbers of nodes and links, where each node and link doesn't mean much in itself, but the way they're all connected together, it means something. So here, say the top cluster of nodes could be all stuff that's kind of about chickens. The bottom cluster is stuff that's kind of about food. You get a whole bunch of links between the chicken nodes and the food nodes. And each individual node and link is part of the overall pattern of chicken or food. And so we have both globalized and localized representation. And then, acting on that store of knowledge, we have a bunch of different cognitive processes implemented as computer algorithms that basically make that collection of nodes and links do different kinds of memory. So you can divide up human memory into a number of categories in a number of ways. We look at declarative, procedural, sensory, episodic, which is your life history, attentional, what you focus your attention on, intentional, what are your goals and sub-goals. And we have specific computer algorithms that cause this network memory to think about the knowledge it's storing in all these different ways. And each of these kinds of memory has specific algorithms, which is its own long story that you could give a whole talk about. Probably, this is getting a little computer sciencey, so I'll probably lose almost everyone except Paul, who already knows everything. But to deal with declarative knowledge, we have a system called probabilistic logic networks, which combines logic and probability theory to deal with beliefs and facts. To deal with learning procedures, learning how to do things, we use an evolutionary learning algorithm, kind of like genetic programming. And I'm not going to try to get across the details here. The philosophical point I want to get across is we don't hypothesize these algorithms are how the brain does things. I could argue that the brain does things that are sort of like these things in some way, but ultimately we're starting from cognitive psychology, from like what kinds of things does the brain tend to do. With this diagram and then a dozen more specialized diagrams breaking down each of these boxes, but that's all psychology. None of that is neuroscience. Then we're asking how can we achieve those psychological functions using computer algorithms. So this last slide here, we've tried to use OpenCog to control a little robot, which I'll talk more about in a few minutes. And to deal with visual perception, we used a hierarchical architecture, which is shown on the left, where the lower levels basically correspond to like 4x4 pixel squares coming into the robot's eye. The higher levels of the hierarchy correspond to larger and larger regions of the visual field. And then we connect that to the semantic network, the sort of concepts like eye, nose, mouth, and we have to recognize patterns like, okay, eyes in a human face are usually next to each other. The mouth is usually below the nose or something. But yet you still want to recognize it. Like, if you saw a picture with the mouth above the nose, you still recognize that's a face. It's just a weird looking face. Right? So, but none of these parts have to work exactly how the human brain does, but there's some similarity. For example, the human visual cortex does have a kind of pyramidal hierarchical architecture like that. But the specific way the visual cortex does it is not the same as the way we do it in our code. So, OpenCog is an open source software project that we created in 2008 by forking some code from my consulting company, Novamente LLC. We've been developing it proprietary before that. Right now, most of the development is going on in a lab in Hong Kong with a collaborative project between my company, Novamente, and Hong Kong Polytechnic University. What we're doing is we're using the OpenCog AI system to control this little video game character inside a world where you can build things with blocks and build towers and steps and try to achieve his goals. The AI is a little robot who tries to get electrical batteries to give himself more power and tries to defend himself against bad guys and so forth. And that's being a good way to kind of prototype our AI ideas. Our next step, I'm working with David Hansen, the roboticist, who has developed this cool little robot called RoboKind. And we want to hook OpenCog up to RoboKind. We're starting to do some preliminary steps there. I mean, RoboKind, it looks kind of like a human. They can smile and make cute little faces, but it's far from having the facility of the human body. But I think that's the direction to go in. And we're looking to take our AI system through all the stages of human developmental psychology. So RoboKind looks like a little kid, and we want to start out that way, make a little robot child, a little video game child, and gradually advance it further and further so it can understand abstract reasoning and understand itself, and ultimately reprogram itself. I mean, if you think about space, what's AI going to do while shooting to Alpha Centauri? Well, it can reprogram its own code over and over again. By the end, it'll either be completely psychotic or a billion times smarter. If we're successful with this project, if our design is workable, we hope we could be within maybe 10 years at the level of having a full-on human-level AGI. I think that is feasible. And whether we really get there depends on many factors. Not only whether our design is workable, but whether we have enough money to keep working on it, and whether someone who hates AI blows us up. There's a lot of things that could happen. Well, I believe we're on a pathway that could work. And in terms of space development, I think AI has the potential to advance very fast relative to space technology. I think the stuff that's happening now with the Google Lunar X Prize and so on is amazing and wonderful. But within a decade, what that is going to get us is, going to the moon, hopefully mining the asteroids if we're really lucky. Maybe putting some guys living in a satellite in L5. I mean, this is all wonderful stuff that has to be done. It should be done. On the other hand, if you want to go out to the stars, that's going to be AIs or robots, unless we invent some teleporters. So my feeling is that we're going to succeed in our AGI research direction well before we succeed in building starships. And quite possibly it will be the superhuman AGIs that develop the starships in the first place. different direction now, whole brain emulation. And most of this material is drawn from the whole brain emulation roadmap that was created at Oxford University by Anders Sandberg, Nick Bostrom, and others. So you can find this document online if you just Google whole brain emulation roadmap Oxford, and it's good reading. I mean, it tries to tell you exactly what steps we need to go through to emulate a human brain in a computer, and then have it live either in a simulation world or have it live in a robot. And I think this is our best chance for getting human beings into space, is take the mind, which ultimately is a pattern of organization rather than a physical system, because the molecules in your body are turning over all the time. You don't have that many of the molecules you had when you're born. And even many of your cells are turning over. You're even still getting new neurons, new brain cells, and old ones are dying. So, I mean, you are not the physical chunk of matter. You are the pattern of organization that produces, or at least correlates with your awareness. And that pattern of organization could potentially be realized in a different physical substrate. We can think about doing this in a variety of different ways. So you can look at what we call level 4 here, species generic brain emulation. That just means making an artificial human. Individual brain emulation, that means making you. Like we can make a Paul Verbos specifically in the computer, not just a human being. And that can be done in various ways too, because it could be an instance of Paul, like a clone of Paul, right? Or it could actually be Paul as he is at this moment. So there's, with his whole life history and memory and so forth. With it, yeah? But entertaining. There's a variety of given scales that we have to deal with here. I mean, going from molecules, synapses, neurons, which alongside glia, astrocytes, and other cells are among the more important cells in the brain, all the way up to the whole brain, which is much bigger. Which scales we have to deal with in order to do whole brain emulation is not quite clear, but the consensus among researchers who are thinking about this a lot is that focusing on the neural network level is going to be okay. There's something that's not true, like Stuart Hameroff has made a name for himself, claiming we would need to go down to the quantum level, or even lower, since he believes quantum gravity is important for brain dynamics, which not many would agree with. So it is possible you have to build a quantum computer to do whole brain emulation. If so, that's not necessarily an objection. We build out quantum computers probably within decades that are highly functional. We have simple ones now. My guess is that neurochemistry is going to be enough. Probably not just a wiring diagram. You need the levels of various neurotransmitters, but I think the molecule level is going to be low enough. And, oh, that's hard to read, too bad. All right. Well, since these slides are, well, the one point to take from this slide is there are 3 main parts of work that have to be done to get whole brain emulation to function. One is scanning the brain, getting the information out of the brain into a computer. The other is figuring out what the hell all that data means, which they call translation in this slide. Going from that big mess of data to something that you can make dynamic and simulate, right? And then simulation is the last part. And scanning right now is the bottleneck, basically. I mean, after we've done all the scanning, the translation may be the bottleneck. Because once we have all the data, we may not be able to understand it. But that's where I hope I can come in terms of using my AI technology to help understand all that data as one of the applications of an AI system. Simulation, we don't know that well how to do either, but computer hardware is advancing pretty fast. And simulation software, while not trivial, there are many working on it. I think it's an easier problem than scanning. I think the hard problem in whole brain emulation right now is how to get the information out of the brain. We have electron microscopy, we have things like the knife-edge scanning microscope. Right now, the most promising tool, I think, is the Athlon, the automatic tape-collecting lathe ultra microtome, which, in essence, you can take a dead, frozen brain, and this will thin slice it into little tiny strips, like the thing at the deli counter at the supermarket that slices meat into thin little pieces. Then it will take a picture of each of those little strips, and then that picture goes into the computer. Then you can use software to reassemble them into a map of what's happening in the brain. Now, there's one advantage that you have to be dead. I mean, they don't yet know how to glue all the strips back together from the back of your head and revive you. That may be a harder problem. On the other hand, if you're going to die anyway, which I hope to avoid doing, which is another story, but if you're going to die anyway, unless you're a cryonicist who believes that your body can be frozen and revived, why not get your brain sliced up and scanned into the computer? So one day be able to revive it in a robot one of these days. So this is the currently most advanced technology, and there have been experiments reconstructing parts of the brain from this sort of data. So this is a 2-millimeter cube from a rat's hippocampus, which is reconstructed from imaging data, which is kind of cool. Now no one has yet taken all the images of neurons and neurotransmitters and chemicals in the brain and reconstructed like a working neural network that does the same thing as the brain. But the technology seems to be there to do that now. It's really just a matter of money to work out all the particulars of the algorithms, get enough computer time, and so forth. So, and then if you look at the right part of this slide, which is the part I want to call attention to, one way to approach this is to start with simple organisms and work up. So David Dalrymple at MIT is working on what he calls the nematode upload project. Take a nematode worm, a very small, simple organism, which has not that many cells, right? And try to get that organism scanned and fully mapped into the computer, into the virtual nematode. And once you've got the nematode going, work up larger and larger. And once you can do a frog, you can probably not far off from doing a person. Although, again, to tell if you've gotten the individual frog right, you have to know the frog really well. It's hard to distinguish your personalities than people will. So, yeah, I think that is the best way for humans to get into space. Emulate yourself in a computer. Now, you have the philosophical question. Once I've emulated Paul, and then we have Paul and Robo-Paul sitting right here. And they're both sitting there like this saying, yes, I'm Paul. Now, do you believe the Robo-Paul that he's Paul? Does the meat Paul believe the Robo-Paul that's actually Paul? But, I mean, the way I think about it, these are philosophical issues that we will in the future learn to ignore. Just as we now ignore all the unresolved philosophical problems of our everyday life, such as, how do I know that any of you have conscious experience at all, and aren't just robots put here to amuse and annoy me? I cannot possibly know that. Yet I assume that you have conscious experience because it's convenient and it makes my life more pleasurable to do so. And in the same way, I think we would assume Robo-Paul had conscious experience, and if I was on the spaceship and it was Meat Man and Robo-Paul, I would quickly come to assume Robo-Paul is Paul on a pragmatic basis. And to me, that's good enough, because I don't think we fundamentally understand anything anyway. But if we do put these whole brain emulations, these uploaded humans on a spaceship, and send them to Alpha Centauri, or better yet, to other galaxies, they're going to get bored. Even as much as he loves math, the Robo-Paul is going to get bored doing nothing but proving all possible theorems for a few 100,000 years. So what do they do? Well, this is where you get into the virtual reality scenario. I mean, you can look at the paradigm example, which is a brain in a vat, which is getting electrical stimuli to make you think it's walking outside in the sun or doing other more entertaining things. Now, I don't think we're really going to put Paul's brain in a vat and bring him on a spaceship. We don't need to. We can just scan his brain and keep a digital image of his brain in the computer. And this is an idea that, of course, was publicized in the movie The Matrix, where they had the incredibly stupid idea of using human beings as electrical batteries. which is kind of funny. If they're smart enough to build the matrix, you think they can build a better battery than the human body. But that's the nature of science fiction. So if we do see whole brain emulations, rather than just AGIs going into deep space, I would predict those whole brain emulations are going to be living in virtual realities. They're not even going to know they're living in outer space most of the time. They'll be romping around in the fields or climbing mountains or seducing each other, doing all the things that people like to do and that they still feel the need to do because they are humans, albeit in digital form. And after a few 100,000 years of that, they may then feel quite odd about going into robot bodies and wandering around on some boring alien planet. But, it could be a long search to find somewhere interesting to go. So it'll be good to have something entertaining to do. And of course, they can also bring along some AGIs to help improve the simulation and make the virtual world better and better. So finally, I'm going to talk about something really weird and a little more directly relevant to space exploration. So I'm going to talk about a potential answer to the Fermi paradox, the question of where the hell are all the aliens? Is it really feasible that we human beings are the first creatures in the galaxy, or the universe, or our local region of the galaxy even, the first creatures to reach a state of technological advancement? I mean, of course, we're all egomaniacs, so we all would like to think that, but how unlikely is that, really? But if we're not the first, then where the heck are all the others? Well, one possibility is that they all blew themselves up as soon as they developed advanced nuclear weapons or synthetic biology or something. Another possibility is they're watching us and waiting to decide if they should wipe us out or not. I mean, all these possibilities have been raised extensively in science fiction. A more interesting possibility to me is that my friend Ray Kurzweil is right, and once technology gets past a certain point, some kind of technological singularity is inevitable, where the singularity is viewed as a point where the rate of advance of scientific and technological progress becomes subjectively infinite to the minds that came before it. Just say, instead of a new cell phone model getting developed every 6 months, let's say it's every minute, until essentially every aspect of technology is advanced faster than we can understand. By that point, the technological advance will be driven by AGIs rather than human beings, because we won't be able to catch up. In terms of the Fermi paradox, the point is, if you had another civilization that, say, 100,000 years ago, reached technological advancement, maybe 100,000, or maybe 100 years after reaching our level of technological advancement, maybe they reach their own singularity. And then, at that point, they may become 10 billion times more intelligent than we are right now. And then why do they care about communicating with us? I mean, we don't spend a lot of time trying to talk to bacteria. They're kind of just a different order of being than us, right? So, John Smart, a futurist in California, who's also a friend of mine, came up with a very amusing idea called the transcension hypothesis. And I'm sure someone else came up with that idea before him, but he wrote a paper about it and gave it this name. His basic idea is, when you get smarter and smarter, presumably you want to keep getting yet smarter and smarter and smarter. It's not necessarily true, but we can take that as a hypothesis. If so, then if our current understanding of physics is basically correct, the best way to get smarter and smarter will be to shrink smaller and smaller. And this is because Einstein's theory of special relativity says information cannot travel faster than light. So if your parts are closer and closer together, those parts can communicate with each other faster, so you'll be smarter and smarter. So if you get a lot of processing elements and pack them closer and closer together, what happens?
It's done at extreme speed.
You become a black hole. So that's the hypothesis. After a civilization reaches past a certain level of intelligence, they pack their processing elements so densely they become black holes. Maybe they're all communicating by some white hole, black hole communication network that we're oblivious to, because we're out here in the idiotic chaotic part of the universe. So we can all build a spaceship and go into the black hole and find out. Then we'll find the theories wrong and get crushed. Another interesting hypothesis, which my friend Hugo de Garis, who's a physicist, has put forward, is along similar lines. You get smaller, and this is the last slide, so you get smaller and smaller and smaller, and in essence, once you become intelligent enough, you implement yourself as not nanotech, but femtotech. You implement yourself as a kind of computer operating on quarks, gluons, muons, intermediate vector bosons, and all these funky little elementary particles. And of course, once you've done that, your intelligence would change in character from what it had been before. You have a different infrastructure. You're not thinking using ordinary logic and probability. You're thinking using quantum probability theory or something even weirder that we haven't understood yet. So another possibility is once a species passes its singularity, it just starts to encode itself in all the random looking to us vibrations of the particles. So where are they? They're not out there. They're like all inside us on a totally different level. And we don't notice them because we can't see that small. And we can't recognize the patterns implicit in their activity because they look random to us because they have a higher information content than our brains can understand. So that's it. One possibility is we build these AGI robots. We put them on spacecraft heading out to Alpha Centauri. While they're going out there, because they're not humans, they don't need to entertain themselves in virtual worlds. They can focus on rewriting their code, making themselves smarter and smarter. But after they get a few years out, they've gotten their own singularity on the spaceship. So they just figure out how to encode themselves in the particulate structure of space-time, like all the other post-singularity beings. And then they don't bother to send a goodbye message to us, and the spaceship disappears. The end.